Alright, so sometimes when solving problems, it may be helpful to manipulate summation notation by separating off the final term or to add a final term to it. Okay, so I will show you how to separate off the last term. Okay, before we look at the application of it. Okay, so given a summation, our index is k, lower limit is m, upper limit is n, and we have instead of using formula, we have specific terms inside. For this illustration, you have term ak. Okay, so this is actually equals to the summation for k equals to m to n minus 1 for ak, and we add an at the back. Okay, um, this should be quite obvious to you because you see on the left hand side we actually perform the summation from m all the way to n. Okay, and on the right hand side we perform the same summation but from m to n minus 1. So if we do not add an, okay, the term an at the back, okay, they are no longer equal because over here we may be doing the sum for, let's say, 10 terms, and over here we may only have 9 terms. Okay, so of course they will not be equal. So we need to add the missing term back into the summation in order to maintain the equality. Okay, so you can actually use a number line to look at this. Okay, so our lower limit is m. After m will be m plus 1, m plus 2, and so on. Okay, our last few terms will be n minus 2, n minus 1, and n. This will be our last term because it's our upper limit. Alright, so essentially what we are saying is that, okay, instead of performing the summation from m to n, that means from start to end, okay, we can perform the summation from m to the second last term, which is n minus 1. That's what we are doing here, okay, for ak. And then because there will be a missing term, we add this term back. Okay, what is this term? This is actually the index, it's not the term itself. Okay, so we're saying that when index k equals to n, the term will be an. So this is actually the missing term, so we add the missing term back in. Alright, so this is what is meant by separating off the last term. Okay, so alright, let's look at actual example. Rewrite k equals to 1, summation of k equals to 1 to n for k over k n plus k by separating off the final term. So you can expand the given summation notation. Okay, if we were to expand this, we will sub k equals to 1 into the formula, okay, to get our first term. So it's 1 over n plus 1, then followed by k equals to 2. So we have 2 over n plus 2, k equals to 3, we have 3 over n plus 3, and so on. Okay, so our final term is n, but for this illustration, instead of working with the final term straight away, we have the second last term. So second last index will be k equals to n minus 1. So we sub n minus 1 into the formula. You have n minus 1 over n plus n minus 1. This is our second last term. And our last term is when k equals to n. This is our upper limit. So we sub k equals to n into the formula to get our last term. Okay, so what we want to do right now is to separate off the final term. So instead of looking at all the terms, we now look at from term number 1 to term number n minus 1. Okay, we will use sigma notation to, we will reduce all this into a sigma notation. Okay, express this entire sum, okay, except the final term using sigma notation. So this should not be difficult because you can basically just read off everything from here. Okay, the only difference will be my ending value or my upper limit, okay, will be this value, okay, n minus 1. So you see the formula remains the same, k over n plus k, which is the same as our original summation notation. Okay, our starting value, our initial value is 1, which is the same as here. The only difference is our ending value. Instead of ending at n, we end at n minus 1. So of course, right now this will not be equal, right? Because we have, let's say you have 10 terms here, you only have 9 terms here. Okay, so they are no longer equal. To maintain the equality, we need to add the missing term. And where is the missing term? Missing term is here. So you can just take this missing term, add it into the summation. So we add the missing term. Okay, then just to beautify our answer, because n over 2n is actually equals to half. So we can just write plus half, right? So this is how we separate off the last term. Okay. Now, adding on the final term. So in this case, we are doing the reverse. We want to express what is given in the question as a single summation. Okay, so right now we have the final term, which is separated. We want to add it back in. Okay, so uh, let's look at the solution for this case. Uh, we have our initial value as 0. Our final term is actually n minus 1. Okay, and over here, this is our extra term which we are supposed to include into the summation. So when k equals to 0, we sub into the formula, you have 1 over 2 to the power 0. K equals to 1, you have 1 over 2 to the power 1. K equals to 2, 1 over 2 squared, okay, and so on. Final term will be k equals to n minus 1. That's my upper limit, right? So 1 over 2 to the power n minus 1. Now, the next term, okay, would be k equals to n. Okay, k equals to n. And that will be 1 over 2 to the power n. Okay, so you can see that they actually follow the same pattern. Okay, which means that we could actually express the entire sum using the sigma notation. Okay, so we can lump all of them into a sigma notation. How do we do that? Okay, again, it's not very difficult because most of the things you can be found in the original sigma notation here. Okay, so our initial value is still 0 from here. Our formula is exactly the same, 1 over 2 to the power k. Okay, right now it's just that we need to include the final term, so our upper limit instead of n minus 1 now becomes n. That's it. Okay, so right now we have an exercise on separating off the last term. You have sigma, okay, sum of k equals to 1 to n plus 1. Our formula is k squared, so we want to separate off the final term. So how do we do that? We first expand, okay, the summation notation. So our initial index or initial value will be k equals to 1. Okay, so when k equals to 1, you have 1 square. Okay, you start into here, you have 1 square. K equals to 2, you have 2 square. K equals to 3, you have 3 square. Okay, and so on. So we purposely write down the second last term. Okay, notice now my ending value or my upper limit is n plus 1. So what comes before n plus 1? N. Okay, so our second last term is k equals to n. So you have n square. Okay, and then final term k equals to n plus 1, you have n plus 1 square. Okay, this is the term that we want to separate off. So it means that we need to uh, express the first term, okay, first all these terms right in front, okay, using the sigma notation. Okay, so to do that, not very difficult. Okay, you can basically copy everything from here. Okay, the only difference is your ending value, upper limit, instead of n plus 1, it stops here at n. Okay, so you have k equals to 1, sum of k equals to 1 to n, k squared. Okay, so no longer equal, right? Left side, right side. Okay, so we are missing a term. You need to add the term. Okay, where's the term? The term you can just read out from here. So plus n plus 1 whole thing square. Okay, so that should make maintain the equality. Okay, you will encounter the need for doing this again and again in when we talk about mathematical induction in section 2.4, okay, at a later stage of this topic.